All right. So in this example problem, we have a crate has a mass of 100 kilograms, and we're asked to determine the uh, the tension in each of the cords in order to hold this this weight in place. So the first thing we're going to do is we're going to draw a free body diagram at the location where all of our forces intersect. So in this case, that's point A. So when we draw our free body diagram, we have to first draw our point, which we'll draw in the center, and then we're going to draw our three axes. So we have our x-axis, our y-axis, and our z-axis. All right. Once we have our three axes defined, we can then define all the forces that are applied at this point. So we have our weight, all right, which was just going to be equal to 100 kilograms times minus 9.81 meters per second squared times k. We'll have a force from point A to point D, which we'll label as force D. We'll have our force that goes from point A to point C, which we'll label as Fc. And then we'll have our force that goes from point A to point B, which we'll label as force B. All right. So with all this defined, we can now define our resultant vector at our point. So at point the sum of all of our forces at point A are going to be equal to is going to be equal to FA plus FB plus FC plus our weight, and we're going to set that equal to 0. So we're going to just define FA, FB, FC, and W in terms of their in Cartesian form. So we'll start off with sorry, it should be FD, not FA here. All right, so we'll start off with FB because it's the easiest. So FB goes along just the positive x-axis, so it'll just be equal to FB I plus 0 j plus 0 k. FC will be equal to its x, y, and z components are going to be equal to f of c times the cosine of 120 degrees, which is alpha. That's the angle between the x-axis and our vector AC, plus FC times the cosine of 135 degrees, which is the angle between AC and the y-axis, and then the last one would be FC times the cosine of 60 degrees, which is the angle between AC and the z-axis. And then the last thing we have is we have f of d is equal to f of fd times the unit vector from point A to point D. So you have fd is going to be equal to r AD, so that's going to be equal to RD minus RA over the magnitude of RD minus RA. So that's going to just be equal to FD times the three components from point D. So point D has minus 1 meter along the x direction. It has a positive 2 meters in the along the y direction, and has a positive 2 meters in the z direction. So if we square all those terms up, it actually comes pretty nicely. you get the square root of 9, which is just equal to 4 meters. 3 meters, sorry. So if you multiply all this through, what we end up getting is we get minus 1/3 FD times the x coordinate plus 2/3 times FD times J plus 2/3 times FD times K. Right? And the only thing that we have left is we have W, which we already defined on the top of our screen here. All right. So we can add these all up to get our resultant force. So if we do that, what we'll end up getting is we'll get, for x, we'll get FB plus FC times cosine of 120 degrees. Cosine of 120 degrees is actually equal to negative 1/2, so we'll get minus 1/2 FC. And then we'll get minus 1/3 FD, and then the weight has no x component, so we'll add a 0 here. And then for the y component, we'll get 0 plus the FC cosine of 135 degrees, which is just equal to negative radical 2 over 2. So we'll have minus radical 2 over 2 times FC, and then we'll get 2 plus 2/3 FD plus 0, and then that would be J, and then for K we'll get 0 plus FC is going to be equal to 1/2 FC. FD is going to be equal to plus 2/3 FD, and then we're going to get minus 981 newtons for the weight. All right. So we can now do is we can set the x component equal to 0, the y component equal to 0, and the z component equal to 0 in order to determine our unknown forces FB, FC, and FD. So we're going to start off with the sum of the forces in the y direction first, and set that equal to 0. So if we do that, what we'll get is minus radical 2 over 2 FC plus 2/3 FD. Alright, so we'll move one of them to the other side, so we'll get radical 2 over 2 FC is equal to 2/3 FD. We'll then say that FC will be equal to 4/3 times radical, it should be 4 over 6 times radical 2 FD, or 2 radical 2 over 3 FD. So we'll use that equality in when we sum all of our forces in the z direction and set that equal to 0. Alright. So if we do that, we'll get 0 is equal to 1/2 times FC. We're going to substitute in for FD here, so we're going to substitute in for FC. So you get 2 radical 2 divided by 3 times FD plus 2/3 times FD minus 981 newtons, and then we can then, if we divide that all up, we'll end up or what we're going to do is we'll get 981 newtons on one side, we'll get FD on the other side, and then our coefficient is going to be equal to radical 2 plus 2 over 3 And then if we solve that out, we'll get FD is going to be equal to uh, 862 newtons. All right, 860. I should be more precise here. 861.985 newtons. All right, we can then use our equality that we had here to solve for FC. So we can say that FC, if we plug in this equation here, we would get FC would be equal to 812.687 newtons. We can take both of these numbers and we can just round them to 3 significant digits. So we would get 862 for FD and we would get 813 for FC. And then the last equilibrium equation we have is the y component. So if we look at the y component of our force vector, we can use that to solve for FB. So we get Alright. So if we do that, what we'll end up getting is we'll get 0 is equal to it's going to be equal to FB minus FC over 2 minus FD over 3. So we can say FB is going to be equal to 1/2 times FC, which is 812.687 newtons, plus 1/3 times 861.985 newtons. If we multiply all that out, we end up getting 693.672 newtons, which we can round to 3 significant digits as 694 newtons. Alright, so to recap what we did in this problem, we originally solved for the tension in each of the chords FB, FC, and FD using our equilibrium equation. So that in order to do that, we had to draw a free body diagram at point A. Once we had our free body diagram at point A, we then defined our equilibrium equation at point A. We defined each of the terms in that equation as Cartesian vectors using the information from the diagram and our unit vectors. And once we did that, we could then sum all our forces together to get the x, y, and z components of our resultant force. And once we did that, we could then solve each of those components equal to 0, and solve for each of the unknowns individually. And we got our 3 answers of 862, 813, and 694 for FD, FC, and FB.